Welcome to the Deep Dive. Today we're cutting through the noise on a fascinating mathematical duo. Concepts that impact everything from weather forecasts to the very buildings we live in. Our mission is to unpack exceedance frequency and return period. Two terms that might sound complex, but you'll find they're surprisingly intuitive and incredibly useful. You'll gain a clear understanding of what they are, how they're connected, and why they matter for predicting extreme events.
Exactly. We'll explore how these concepts help us quantify risk, especially when dealing with those rare, impactful occurrences, providing a foundation for critical thinking about future events.
Okay, let's dive straight into exceedance frequency. For listeners maybe familiar with basic probability, how would you sort of frame this concept? What makes it distinct?
Well, at its core, the frequency of exceedance, sometimes called the annual rate of exceedance, it just describes how often a random process goes above a specific, usually quite high critical value.
Right, a value far from the average.
Precisely. We're talking about extremes here.
And how do we actually measure that? Is it just, counting every time it happens?
There are essentially two main ways people count it. You can count the number of peaks of the process that go beyond that critical value.
Okay.
Or you can count upcrossings. That's when the instantaneous value actually crosses the critical value, but specifically with a positive slope moving upwards through it.
Ah, okay. Is there a big difference?
For many practical purposes, especially if the process is, let's say, well-behaved, or if the critical value is very high, they're often considered pretty much equivalent. You assume one upcrossing, one a peak per exceedance event.
Makes sense.
But if you have a continuous process with lots of high-frequency noise, you might actually see multiple little peaks or upcrossings very close together for what feels like one single event. So the distinction can matter sometimes.
Right, okay. So we're essentially mapping out these moments, these extreme spikes when a threshold gets crossed. How does this translate into the real world? What's the use?
Oh, it's absolutely crucial for predicting extreme events. Think about major earthquakes, severe floods, or even the kind of intense gust loads an aircraft might experience in flight.
Turbulence, yeah.
Exactly. It's kind of the math behind why that happens or why we need certain building creeds. It helps us quantify, put a number on how often we might expect such events to occur.
Okay, so we've got a handle on how often extreme events exceed a certain level. That seems to lead us naturally to return period. Lots of people have heard this term, especially with things like 100-year floods. What's the definition there and how does it connect?
Yeah, the return period, sometimes called a recurrence interval, is basically the estimated average time between occurrences of an event of a certain magnitude or greater.
Average time, okay.
So a 10-year flood, for instance, is an event with an average recurrence interval or return period of 10 years. And what's really neat mathematically is that the return period is simply the reciprocal, the inverse of the frequency of occurrence we just talked about. So if an event has a frequency of, say, 110 per year, meaning it happens on average once every 10 years, its return period is 10 years.
Okay, right. So a 10-year flood has a 1 in 10 or 10% chance of being exceeded in any given year, and a 50-year flood, that'd be a 2% chance each year.
Precisely.
But this is where I think a lot of confusion comes in. I've heard so many people assume a 100-year flood means it happens, exactly once every 100 years, like clockwork. Can you maybe debunk that for us?
Yes, that's a really common and very important misconception. It's critical to understand this. Despite the name, a 100-year event does not mean it happens exactly once every 100 years.
Right.
Or even that it will only happen once within any specific 100-year period. It's purely a statistical probability for any single year. In any given 100-year stretch, you could see a 100-year event occur once, twice, maybe several times, or perhaps not at all.
It's just based on probability each year.
Exactly. And this distinction matters a lot because our estimates, they're based on historical data. Think about it. If we only have, say, 400 years of river flow records, the biggest flood we've seen in that time might get statistically labeled as a 400-year event based only on that data. But what if we suddenly had 1,000 more years of records? We might see much bigger floods.
And that original one wasn't so rare after all.
It could be reclassified, yes.
Yeah.
That's why for truly rare events, things we haven't even observed yet, like maybe a hypothetical 1,000-year event, we absolutely have to rely on statistical models. The historical records alone just aren't long enough.
Okay, that makes perfect sense. So if it's not guaranteed to happen once in that time frame, what is the actual probability? Like, what are the chances of a 100-year flood happening at least once during any given 100-year period, that feels like something really useful for people to know.
Yes, that's a fundamental question.
Yeah.
And it leads to some interesting statistics. For many kinds of random processes, particularly as that critical value, the threshold for the event gets really, really high.
For those rare events.
Exactly. For rare events, the number of times the threshold is exceeded starts to behave like something called a Poisson process. This is a very handy statistical model for describing rare independent events happening over time.
Okay, the Poisson process.
And if these events follow a Poisson process, we can actually calculate the probability that a specific critical value, let's call it Imax, is exceeded at least once by a certain time, t.
Right.
The formula turns out to be 1 n max. Now that Nmax there, that's just our frequency of exceedance for that specific value Imax.
Which you said is 1 over the return period.
Precisely. So Nimax is 1t, where t is the return period. So the probability simplifies really nicely to 1 ET. The key isn't maybe memorizing the formula, but understanding what it tells us about how these chances add up over time.
And this leads to what I think is a really fascinating insight, the number that comes out of this.
Indeed. This is quite revealing. For any event, whatever it is, with a given return period t, the probability of that event occurring at least once within a time period that's equal to its own return period. So when t equals t in that formula,
Okay.
that probability is approximately 63.2%. It comes from 1E1, which is about 0.632.
Wow. So let me get this straight. For a 50-year flood, there's actually about a 63% chance of a flood that big or bigger happening within any given 50-year period.
That's exactly right. It's not 100%, it's not a guarantee, but it's a substantial likelihood. Over 2/3 chance, roughly.
That 63.2%, that really is an aha moment. It completely reframes how you should think about these 100-year or 50-year labels, doesn't it?
It absolutely should. It highlights that these aren't deadlines. They're statements about annual risk that accumulates. Now, while the Poisson distribution is generally seen as the most logical way to interpret return period, one could technically use other models, like the binomial distribution. But for practical purposes, especially when you're dealing with rare events, which means low annual probabilities and often long return periods, the results you get from both models end up being very, very similar. That 63.2% figure is quite robust.
Okay. So moving beyond the fascinating math here,
Yeah.
what are the big practical implications? Where do we actually see exceedance frequency and return period being used out there in the world?
Oh, they're absolutely fundamental for risk analysis in so many fields. Engineers and scientists use them to estimate the probability of major earthquakes hitting a certain intensity.
Right.
They're used to improve weather forecasting, especially for extreme weather events. They're critical for assessing the loads on hydraulic structures. Think about dams, levees.
Things you really don't want to fail.
Precisely. And even in aerospace, calculating potential gust loads on aircraft wings to make sure they have the right structural integrity, the right safety margins built in.
So it underpins a lot of safety calculations.
Absolutely. If you connect it to the bigger picture, knowing this probability of exceedance is just vital for engineering design and for public safety planning. When engineers design a bridge or a skyscraper or even a storm drain,
Yeah.
they use these calculations. They estimate the probability that some extreme event, a massive flood, a really strong earthquake, hurricane force winds, will exceed the limits the structure was designed for sometime during its expected lifespan. It's all about building in resilience based on calculated risk.
So as you can hear, exceedance frequency and return period are really far more than just, abstract mathematical terms. They're absolutely critical tools. They help us understand, and maybe more importantly, plan for those rare but really impactful events that shape our world.
They really offer a probabilistic way of looking at the future. It acknowledges that while these extreme events are, by definition, infrequent, they are never actually impossible, and we can quantify that chance.
And that leaves us with, I think, a pretty provocative thought to mull over. Knowing what we now know, that any T-year event actually has about a 63.2% chance of happening within its own return period. What should that really imply for how we prepare? How should our communities and infrastructure plan for things we consider rare, natural occurrences, knowing the odds within a typical infrastructure lifespan are actually that high? It certainly shifts your perspective on long-term planning, doesn't it?